So we continue our discussion of force and momentum, right? And so let's start by writing our force equation again. So F was dp over dt, right? Now let us say that instead of a point particle or point object, I have a system of particles, right? So multiple objects which are interacting, could be interacting with each other. So there is also a force between these objects, and there is an external force on each of these, right? So this is my XYZ coordinate system 0, and for here, let's say I am taking about 4 particles, right? Randomly distributed. So I am not looking for a particular pattern here. And for each particle now, what I can do is I can assign a mass. So M1, M2, M3, M4, as well as I can assign a position vector, right? So R1, similarly this will have R2, this will have R3, this will have R4, right? So this is my system of particles, and now I need to write down the equation of motion for this system of particles, right? So what I have to do is I have to first consider the forces acting on this, and then the motion of each particle, right? And the combined motion will then describe how the system is going to move, right? So what are the forces? 1, forces between particles, right? And so we'll see in nature that somehow it so happens that the forces that we are going to consider are all two body forces, right? So that means basically what I am saying is there is a force, and let's say if it's a gravitational force, then a force acts between M1 and M2. So M1 pulls in M2, M2 pulls in M1. Similarly, there is a force acting between M2 and M3, M1 and M3, M1 and M4, M4 and M3. So pairwise, right? So there are two body forces and nothing more complicated. So forces between the particles, and now I can write down these forces as F12, F13, F23, and so on, right? And second is external force acting on the system. So again, so let's say on individual particle there are individual forces acting. So I can write down this as F1 external, F2 external, and so on, right? And of course, when we try to combine this, we have to combine this vectorially, and we can get the total force, right? Now, so now let's find out the total force acting on the system. And now the total force, so F total, and now I'll write the vector, is sum of all external forces. So I equal to 1 to n, let's say there are n particles, plus, now this is slightly important because these are two body forces. So sum over I equal to 1 to n, sum over j equal to 1 to n, where I is not equal to j. So we are looking for different pairs, any number of pairs that you can form here, and forces of the type Fij, right? And well, let's do the vector form. Perfect, right? So these are two forces acting on the system. Looking here, this is the external force. This will be basically then taken as the total internal force, right? And now what we can say is, if it is a two-body force, then we know that F12 is simply equal to minus F21. If M1 pulls in M2, M2 will pull in M1, gravitational force. If the electromagnetic force, then, and let's say these are the same charges, then M1 repels M2, and then M2 repels M1 with the same strength, right? So this is the property, and what happens is, because of this property of these two body forces, that they are equal and opposite on both the bodies, this total term will basically cancel out when we sum over all these particles, because each pair is interacting with each other is interacting with this kind of force. So total F internal is actually 0 for any system of particles, and what that gives us is F total is then basically just the total F external. So it's only the external force which affects motion of the system, and now this is then dp over dt. So this is a very important result, which I think I also mentioned when we were discussing force. But now here it comes out nicely that first of all, well, now a system of particles, a individual particle, whatever, its motion is only affected by the external force acting on the system. So even if you have the system made up of multiple particles, the internal interaction between these particles is not going to change the state of the system spontaneously until there is a external force acting on it, right? So we can write it down like this, and now what we can do is we can also get individual momentum components. So this P, which so far is simply representing the total momentum of the system, right, is also made of individual momenta. So so now I can extend this as F external total force is d over dt sum over I pi. So the momentum of individual particle in the system, right? And then you simply sum over the entire thing. So then this becomes my force equation, right? Okay. Now what we can do is, looking at that force equation, so looking at this force equation, and okay, so let me first write down F external as I defined as d over dt, and then I'll sum over I, and let me write down mi ri dot, right? So just like, so I'm writing P momentum as mv, where v is simply ri dot. So and now mi are the masses of these individual particles, and ri are their position vectors. So ri dot is their velocity vector, right? Already particles. So this is so far this is correct, right? Okay. Now we also know that this equation we could have written as ma, right? We attempted to write it as this, and in many cases this is more or less the correct equation, and I can write it down as mr double dot, so some acceleration vector, right? I'm going to do it. So let's say, can I represent this equation in terms of that? So we are saying that this is equal to some mass now, right? And because now we don't know what is the mass of the entire system or how to treat the mass of the entire system, so some mass and Ri. So another acceleration vector r double dot related to some position coordinate r, capital R, right? So you want to write it out like this. Now of course we can do it in a simpler way, and we can get the familiar expression if we say that mi or individual mi's are constant. So whatever process we are studying, whatever dynamics is happening, the mass does not change. It's a system where we are not changing any mass, right? And we know that this ma is only valid or truly valid if the mass is actually a constant, right? Otherwise, this is the accurate equation. So if this is the case, then now I can take this and write F external, and sometime I'll just drop this external term because now we established that forces, it's only the external forces which are going to act. So d over dt sum over I now mi ri dot, which then I can write down as sum over I mi d over dt of ri dot, because mi is time independent, so ri double dot, right? And this is what I want to be equal to some mass m r double dot. So this is acceleration, right? And if this is the case, then the way I write it is r double dot is sum over I mi ri double dot over m, where this m is total mass of the system. So if this is the total mass of the system, of course I can also write it as sum over mi, right, this mass. So now this becomes an equation which relates the position coordinates or the position vectors of individual particles to a hypothetical vector r, right? And I mean, of course, we can take the back integral and get this directly into the position vector nomenclature. So with the hypothetical vector r, and you can already guess where am I going with this. So we are going to write down this vector r as sum over I mi ri position coordinates sum over I mi, and this is your, and then we'll term it as center of mass of the system, right? And what this center of mass system basically describes in terms of this equation is that an external force acting on the system of particles, right, effect of that is same as if the total force acting at some hypothetical point r, whose position vector is r, right, and the total mass of the system is concentrated at that point, right? So basically a system of particles or an external object, as long as its effect or as long as effect of external force on it is concerned is reduced to a point particle with some coordinate vector r and total mass m, and as we have shown, the force equation remains exactly as it is. So this is called the center of mass coordinate, right? And of course now what one can do is one can take some different shape objects and try to find its center of mass. Right. So again here, if system is made of discrete particles or discrete objects, right, then the RCM is basically summation I mi ri over summation I mi, right? However, if the system under consideration is an extended object, such as a rigid body, which we are going to discuss later, right? Is an extended object, then basically what do we mean by extended object, right? So what we mean is that limit mi tends to 0. So basically what I am saying is I have some sort of an extended object and I can have multiple points. I can take any position vector here, and that does connect to a very infinitesimally small mass mi, and how many such masses make the body? So it's like infinite. So I tends to infinity. So if mi tends to 0, I tends to infinity. In that case, and under that approximation, we can write down RCM as, so basically we are going to replace summation with a continuous integration. Is integral r dm over integral of dm. Integral of dm will give us total mass, and this basically then gives us the it points to the position vector of that infinitesimal element, and then extended over, integral will be extended over the entire object, and this will give us the center of mass of the system. So let's try to calculate it for a couple of simple cases, right? And then maybe we can practice more. For time being, I am going to do this only in the Cartesian coordinate system, and later on we will see how we can extend the same approach to other coordinate systems. Okay, so let's take example 1, right, in this case, and we are going to find out center of mass of a rod, right, a uniform rod, a rod of length L. So again, let us say this is my X, this is my Y. I am starting with a rod because what it means is that effectively my problem becomes a one-dimensional problem, right? So let's say this is my rod, and it's perfectly symmetric in the other YZ, and it's a thin rod or whatever. So then all I am concerned is with the length of the rod. So let's say this is L, of rod of length L, right? And total mass is, let's say, M, right? So first what I'll write down is mass per unit length of this rod lambda is basically M over L, right? This is the mass per unit length. And now I am going to do this integration. So I'll select a very small region of length dx at a distance x from the origin. So this is my origin, right? Arbitrary origin, at a distance x from the origin. And so that's your dm. So let's find out what is the so mass of an element of length dx is dm equal to the mass density into length of the object, so lambda dx, and then RCM for this rod is then, it's an x coordinate only, so integral at a distance x, and then x goes from 0 to L, so 0 to L x I cap lambda dx upon, well, integral dm, so lambda dx, right, 0 to L. So that is the integration that we need to do. Integral 0 to L lambda dx, right? Okay, so we can now do this. It's very simple. So lambda is constant, right? It can be taken out. Here lambda is constant, can be taken out. So this will simply cancel out. In fact, this term is only going to give me total mass, right? So let me write it down. So let me cancel this out, and then so this will be integral 0 to L x dx upon integral 0 to L dx, which gives us x square by 2 0 to L upon well, x and 0 to L, so upon L, and this is then L by 2. And of course we forgot our I cap here, so I cap follows us everywhere just to make sure that this remains in Cartesian coordinate. So L by 2 I, so RCM, right, is L by 2 I cap, and what is L by 2 I cap? It's the midpoint of this rod, right? And of course we know that if it's a uniform mass density rod of length L, then its center of mass is in the middle of the rod, right? So of course we can find out a lot of these things using symmetry also, right? But this is the formal procedure of finding it. Okay. Let's take one more example on the similar lines. Okay. And what I'm going to do now is I'm going to extend this problem into 2 dimensions. Okay. So now let us take center of mass of a rectangular plank, right, or plate, doesn't matter, right? And now again, if it's a uniform, the density is uniform, then the third dimension is, and the third dimension is not is very, very small compared to the other 2 dimensions, then we can take this problem as a 2-dimensional problem. And again in that 2-dimensional system, what we'll have is, so now we'll have our x and y coordinate, and we choose this such that one corner of this rectangular plate lies at the origin. Let's say its length is L and its breadth is B. Okay. And so now we have to find center of mass of this system. So let us take again a very small, a tiny mass element dm, right, at a distance x and y from here with extensions dx and dy. So this is a small mass element of area dx dy, and now let us say it is located at some position vector r, which is basically xi plus yj. Okay. So now we have to find out the center of mass using this construct. So again, what we will do is we will write down mass per unit area now in this case, right? Sigma, let's say, and this is equal to the total mass of the plank divided by the area, so L into B. This is the mass per unit area. If this is the mass per unit area, then what is the mass of small element of area dx into dy? Right? So that is my dm is equal to sigma dx dy. And if this is the mass of the small element, then now I can write down the RCM as integral. So now, since the problem is in 2 dimensions, basically we have to integrate in x coordinate as well as y coordinate. So we'll have 2 integrals. Right? So for a 2-dimensional problem, we'll have 2 integrals. One in x, 0 to L, one in y, 0 to B. The coordinate r, which is x I cap plus y j cap, and the element dm, sigma dx dy. Right? So this is my RCM, of course divided by integral of sigma dx dy over the entire length and breadth of the plank, but we know that it's just equal to the total mass. So divided by m. Now this can be now written as 0 to L. We'll just break the components separately. 0 to B, x sigma dx dy I cap plus the same 0 to L, 0 to B, y sigma dx dy j cap. Right? So, and of course this entire thing divided by m. Okay. Sigma can be taken out, so this simply becomes sigma over n. And now we can do the integration. So now again, since x and y coordinates are independent, the integrals also can be done separately. Right? So we don't, so there is no mixing acid there. So basically, x dx will be solved and dy in this case will be separately y. So this will give us x square by 2, 0 to L into B, I cap plus this will give us y square by 2, 0 to B, L j, and of course that will be divided by here. So now we'll put the limits. So we'll get sigma over m. Right. You should check this. LB will come out, and I'll get here L by 2 I cap plus B by 2 j cap. Okay. You can see that the entire this thing is going to go to equal to 1, right? Because sigma was m over LB, so we'll have sigma m over LB. LB is here, m is here. This will all give us 1. So the center of mass coordinate RCM for rectangular sheet is given then as L by 2 I cap plus B by 2 j cap, right? Which is what? L by 2, this is L by 2, in I direction, this is b by 2 in j direction. So center of this sheet, right? Which is again rather obvious that if it's a uniform or plane sheet, then center of mass is going to lie at the center of the sheet. But in the formal procedure, we can get this. Of course, once we know this formal procedure for any arbitrary random shape or for objects where the density is not a constant, right? For example, in this problem, if let's say it was given that the mass density is not this, but it's something like sigma equal to sigma 0 xy, right? Well, not sigma 0 xy because it has to be dimensionally correct. Next is sigma 0 xy over LB, right? If this would have been a density profile, then still the analysis goes exactly like this. Instead of sigma being constant, then which we took out of the integration, we have to put the dependence of sigma on xy in the integral and just simply solve it, right? And then we can get what kind of where the center of mass will lie on this system.